This video demonstrates the pilot scenario 2.5, which showcases how ELECTRON detects cross-domain attacks against critical electrical power energy systems, which can affect the electric vehicle charging infrastructure. As a charging station operator, Public Power Corporation, or PPC, manages multiple electric vehicle charging stations in multiple geographical locations. The EV charging networks are functional, thanks to the proper operation of a complex electrical power energy systems network that consists of power generation systems, transmission systems, and distribution to end users. However, in this interconnected ecosystem, any significant anomaly or cyber attack across the energy chain may affect the EV charging network. For example, a cyber attack against an electricity substation, operated by the Independent Power Transmission Operator, or IPTO, may affect the power supply of the connected EV charging stations operated by PPC. Moreover, it is remarkable that threats with similarities can be found across the energy chain. Considering the above, this scenario focuses on demonstrating the detection of two cyber attacks, against a charging station management system, and against a remote terminal unit of a substation, thus showcasing that ELECTRON can detect inter-domain attacks that can indirectly threaten the EV charging systems. For the first attack, we are focusing on an OCPP session establishment denial of service attack, which targets the EV charging station management system, or CSMS. According to the OCPP protocol, a session between the EV charging station and the CSMS is initiated by the EV charging station. If the connection is accepted, then the EV charging station sends periodic heartbeat messages to indicate its availability. If the connection is not accepted, usually because the charging station has not been pre-registered by the administrator, the CSMS must respond with an HTTP 404 not found message. Exploiting this behavior, an attacker could flood the CSMS with fake WebSocket requests, thus forcing the CSMS to respond to each one of them with an HTTP 404 message. As a result, this activity could lead to depletion of network and computing resources of the CSMS. For the second cyber attack, the attacker targets a remote terminal unit, or RTU, of a substation automation system. In particular, the attacker executes a CSENA1 packet flooding attack, utilizing the IEC 104 network protocol. According to this attack, the adversary aims to overwhelm the targeted RTU with setpoint requests. This activity could render the RTU unresponsive, thus causing potential cascading effects to the electricity grid and interconnected sectors, including the EV charging domain. Considering the aforementioned, the goal of this scenario is to demonstrate how ELECTRON can detect both OCPP and IEC 104 cyber attacks, which share similar characteristics, in terms that they both aim to flood the target system with network traffic. This is the testbed architecture employed by PPC and IPTO for this scenario. The testbeds replicate an EV charging station area and a substation automation system respectively. The EV charging area includes multiple EV charging stations, both real and simulated, as well as the charging station management system, which is the target of the attack. The substation testbed consists of an RTU and a substation supervision station that monitors and interacts with the RTU. In both locations, the ELECTRON FLIDPS is deployed and monitors the network traffic for suspicious activity. Starting with the IEC 104 case, we now see the simulation of the normal operation, where the substation supervision station periodically queries the RTU for measurements. For this purpose, the Q-Tester 104 open-source software is used. Next, from another host, the attacker utilizes the same software in order to flood the targeted RTU with setpoint commands. To this goal, the attacker uses a custom Python-based graphical user interface automation software, which automatically operates the Q-Tester 104 accordingly, in order to achieve the flooding. On the RTU dashboard, we can see that the RTU device indeed receives an unusually high amount of IEC 104 commands. Moving on to the OCPP DOS attack, the attacker utilizes a custom Python script, which leverages the Python WebSockets library, in order to simulate a botnet of EV charging stations. The attacker spawns 100 execution threads, each imitates an EV charging station. Each one tries to start a WebSocket session with the CSMS, pretending to be a legitimate EV charging station, and uses a random EV charging station ID. Since the EV charging station ID is unknown, the CSMS rejects the connection, but the EV charging station bot tries again, by randomizing the ID. The scale of the attack is further increased, by spawning 10 processes of the Python script, thus simulating 1,000 EV charging stations with this behavior. Ultimate goal of the attacker is to cause exhaustion of computing resources on the CSMS, thus preventing legitimate EV charging stations to be served. It can be observed, from the container management system, that the utilization of computing resources rapidly increases, while the attack is ongoing. Moving on to the FLIDPS, the component analyzes the network traffic and successfully detects the IEC 104 setpoint DOS attack. As a result, FLIDPS generates the corresponding security events. The security events are received by the ELECTRON SIEM, which aggregates them, and generates corresponding security alerts. In a similar manner, the FLIDPS component analyzes the network traffic and successfully detects the OCPP DOS attack. Each time the attack is detected, FLIDPS generates the corresponding security events. Then, the ELECTRON SIEM receives the security events and normalizes them. The ELECTRON SIEM associates security events together, thus forming security alerts.